Good evening all. Welcome to the week 8 live session for optimization from fundamentals course. To those of you who are joining for the first time, I'm Durga Prasad. So I'll be the PA for this particular session. The main objective of this session is to help you solve your assignment problems. And if you have any queries, we can discuss them over these live sessions. These will be organized on every Saturday from 5 to 7 p.m. Of course, you can always post your queries in the discussion forum as well. We'll wait for a couple of minutes for a few more students to get to join, and then we'll get started. Hi, good evening. Yeah, fine. How are you doing? We'll get started at 5. Wait for one more minute and we'll get started. So how do you find the course? How do you find the course? It's good. Okay. So you have some doubts? Okay. Okay. Except for the derivations, you understood why we are doing this stuff, right? So maybe I'll just discuss why we are doing this stuff. Like what exactly is it? Derivation? Yeah, yeah. So, yeah, sure. Okay. Then we'll get started. It's around 5. We'll get started. Good evening all. So this week's topics include the definitions of tangent cones, and then why should we study tangent cones and how are they related with optimization problems. And then we discuss something called active constraints and how to define them, what exactly are these active constraints. Then we'll try to understand what the constraint qualification theorems are. And then we'll go to KKT conditions. Essentially, I'll just illustrate what the conditions are. I'll just state the conditions, and then we discuss what is called convex function and how these KKT conditions, when applied to convex function optimization, can help us simplify some of the problems. And then we'll discuss some of the problems at the end of after we discuss these topics. So the first concept is the tangent cones. So the definition goes as this, where the tangent cone is denoted by this, where x star is a point and S is a feasible region that you want to feasible region. Then we define the set of vectors D, where D here is a vector such that there exists a sequence xk belongs to this feasible region. So if you have a feasible region, so let's say this is my feasible region, and I have a point x star. So what we are doing is we are collecting a sequence of points xk in the in the feasible region. So let's say these are my points x1, x2, so on, and you keep going to xk as you get the sequence like by some iteration or something. So initially you start with some guess x0 inside the feasible region, and you use some algorithm and move to x1, so on till you go to the optimal point x star. So all these points, whatever is there in the sequence, are denoted by this xk. We assume that this xk will eventually go to x star by whatever process you are generating all these xk's. They will eventually go to x star, and you also define another sequence tau k, which varies from 0 to infinite, and that is actually going to 0. in that particular case, as tau k tends to 0 and as xk tends to x star, we define the vector d as limit k tends to infinity, this particular one. You can think of this as, let's say in this domain, let's say xk is somewhere here. If x star is the origin, xk minus x star will be something like this. So it will be a vector pointing in this direction. So this vector is this particular d. Now I can have xk in different directions. So I can have xk here, I can have xk here. So all these directions, this direction, this direction, this direction, all these directions, all the set of all these directions is what we are calling the tangent point at that particular point. Now again, you can have different points depending on the x you are choosing. You can, if you choose x here, then it will be there's a set of vectors like this. All the set of these vectors will essentially form my tangent cone. Now if you have a point on the boundary, that's where the definition comes into picture. Here we need to choose the points xk such that all of them belong to the feasible region itself. So here I can take a vector like this, but something if I take like this, then this vector can't be included because that falls outside the domain. So the max you can go is up until this one. A vector like this is, which will be the tangent to that particular point, tangent to that particular feasible region at that particular point. So all these vectors which fall in this, all the vectors here, whatever vectors that you can form inside this will form my tangent cone for the boundary points. So what we are essentially doing now is, once you define a tangent cone for a point, if the point is an internal point, then it will include all the directions that are possible in that space. In that space, in the sense, when we define the feasible region, we define in terms of some inequalities in some domain xi. So that Rn, so tangent cone will be equal to Rn if it is an internal point, and when it is an external point, it will include all the points that are falling inside the feasible region. So what do we do with this? So once this is how we define a tangent cone, and then the main point here is when you have multiple surfaces. Say why we are trying to do all of this, we will get clear. Once we get that clear, then we'll get back to here. Why should we study these tangent cones? Is because as we started initially, we have a function, objective function that we want to minimize or maximize, whatever you are trying to do. But let's say we are trying to minimize a function. You can always convert it into maximization problem. So there are infinite number of points in the feasible set. We don't want to check each and every point. We have to somehow filter these points and narrow down our search space. So how do we do that? Like previously we thought about first order sufficiency, first order condition, second order condition. We take derivative of f of x equal to 0 and all of those things. But then all of them were good enough for, let's say, an unconstrained problem. Like the first order conditions were derived for unconstrained problem. How do we tackle the case of a constrained problem? Especially instead of having an unconstrained domain, you have x limited to s. Now you cannot search over the entire space x belongs to minus infinity to infinite, but there is only a certain number of points that you have to search for, and they belong to a set S. So when things like that arise, we need to come up with a different way to deal with the filters. How do I filter it? I cannot directly use del f x star equal to 0. For example, let's say you have, this is my domain. Let's say the function value here is say 10, and the function keeps on decreasing as you go along this direction. Let's say at this point it is 9, at this boundary it is 8, at this point it is 7. If it is unconstrained problem, when I try to minimize, then it will keep going in this direction. And I'll find, let's say somewhere it goes to 0 and again it starts to increase. Let's say the function value is something like that. If it is an unconstrained problem, then when you make the del f x star equal to 0, I will eventually reach this point and I will say that this particular point will be my minimum. That is where the minima has occurred. But now when we have a domain, like I need to find only the point in this domain, I cannot directly use del f x star equal to 0. Then I need to come up with something else. Now with the definition of tangent cone, whatever we have defined, the vector d. Now if you think of it, what is this d vector saying? So the d vector essentially is between xk minus xk star by tau k. So that is something like this. So if you see, as I go along the d vector, what is happening? I'm going towards the interior point of the feasible domain. So whenever the point is lying on the boundary, I'll go towards the interior. So if, for example, the value of the function is minimum inside the domain, then del f x star will be 0 inside, so I don't have to worry about it. But let's say if it is outside the domain, then what can we do is essentially you go along the direction in which the function is minimized. So essentially that means you're going in a direction along which del f decreases. But then once you reach this point, at this point, if del f x, if the gradient of f is decreasing as you go outside, which means all the points beyond that are less than this. So this particular point will be the local minima, because if you go inside, if you go along this direction, the function value will keep on increasing. So the minima that will occur over this domain will be this particular point. So to state that mathematically, what we do, we take gradient of f. So that will point in this, that will be pointing outwards, and then we take the tangent cone d, and we say that when you multiply both of them, when you take a dot product of both of them, so what will this, if the gradient is decreasing in the direction that you are moving along as you move towards the interior point, so if this product is positive, it means d is positive when you move towards the interior, and del fx is positive if the value of function increases in that particular direction. So as the function increases, if you move towards the interior of the domain, then this particular point will be the minimum. So there are two conditions. This is essentially can be broken down into two conditions, where you have equal to 0 or you have greater than 0. When this particular thing is equal to 0, then it essentially means del f x star equal to 0. So for all the interior points, we have just seen that d will never be equal to 0. If a point is interior, then the set of all vectors will be Rn. All the vectors will be there. So d will not be equal to 0. So del f x has to be 0. That we already know from our first order condition. Now, if it is at the boundary point, if the minima occurs at the boundary point, then you have this particular product to be greater than 0. Because only if that is like that, if you go outside the boundary, the value will be minimized, and the best minimum that you can get on this domain is this particular boundary point. That is what this theorem says. So once we know how to calculate d, if we calculate d, then all we have to do is, for all the points inside external, whatever you do, you calculate this particular quantity, and then see whichever point this particular criterion satisfies. Out of those points, one of them can be the minima. There can be points when this condition is not satisfied and you can have minima, but this is not like a necessary if and only if kind of a condition. But if x star is a local minima, then this has to be satisfied. The other ways may not always be true. So now with this definition, when we have multiple constraints, so as I said, S is basically my feasible region. So this is my feasible region. So how do I represent this feasible region? I write certain set of equations and then say like like we have seen the set of inequality constraints. When we have inequality constraints, we take G1, G2, G3, all these inequality constraints are like, for example, you can take something like x plus y equal to 1, and then take x equal to 0 and y equal to 0. Let's say this is y equal to 0, this is x equal to 0, and then this is say x plus y equal to 1. So if I put them as inequalities, x greater than or equal to 0, y greater than or equal to 0, and x plus y less than or equal to 1, with these inequalities, this is my feasible region. So the feasible region S is, again, you write it in terms of certain equations, and then you will put that inside your optimization problem. So this is how you define it. So when we define it in this particular way, we have multiple half spaces or multiple such equations. So we need to find tangent cone for the intersection of all these things. But in general, when you take tangent cones to multiple surfaces, that may not be equal to the intersection of tangent cones to all the surfaces. So what I mean is like you might have something like 3-4 surfaces like this, and this is the region you are interested in. So what we can usually think is okay, to find the tangent cones of this region, what we can do is first find the tangent cones of, let's say this is 1, then we'll find tangent cones of 2, then we'll find tangent cones of 3, and then take intersection of all these tangent cones, then we get a new set, and that new set may or may not be equal to the tangent cones of this particular surface. There are a special scenario where they will be equal, and that is what we will be discussing next. Okay. So up until here, is this clear? So why we need tangent cones and what exactly is the definition of a tangent cone? Are there any queries in this? Clear. Okay. So now yeah, you can unmute yourself. Why is it not an if and only if condition? Okay, I just seen the message. Okay, so let's say you have something like this. Maybe it's not a convex function or some kind of a weird shape where you do not have this particular point. Maybe I should draw something. 1D, then it may be clear. Or maybe let's take something else. So all you let's say let's put it in this way. So you wanted to let's say this condition is satisfied. Let's say you have the gradient of f times t greater than equal to 0. Let's just take the one case equal to 0. If that equal to 0 in for any interior point, grad f equal to 0. So even when you have grad f equal to 0, that can happen in different scenarios. Even with grad f equal to 0, depending on whether your del square f is positive or negative, that can be minima or maxima. Like just having this condition equal to 0 doesn't necessarily guarantee you that that will be a local minima. Like we have discussed it, even in for an unconstrained problem. So this is like if it is a local minima, then this condition can be satisfied. But if it is, there can be other points where this can be 0, but it may not be a local minima. Maybe it is a local maxima or something. It can be a saddle point or something else. Does that answer your question? Yeah. Yeah. The next concept is the concept of is active constraints. So we formulate the problem as minimize f of x such that you have certain number of constraints, and let's say all these functions are C1, it is continuous and differentiable. Then what are active constraints is basically out of all these constraints, the constraints for which you choose a point. First you choose a point. Let's say x star is a point, and if at x star, GA of x star, you can have two scenarios. They can be less than 0 or exactly equal to 0. Out of these two scenarios, if it is exactly equal to 0, then that means you are on the boundary of the constraint. So again, each of the GA of x I can draw in some plane, depending on if it is R2, then I can draw in something like this. So this is say G1, this is say G2. So this domain, whatever is this side, this is G1, and whatever is on this side, let's say this is G2. So for Z1, if a particular point is lying here, then this particular point, let's call it x1, or let's say x itself, or x star. Let's say x star. X star is this particular point. This particular point is lying on G1. So for this particular point, G1 of x star will be equal to 0. So at that particular x star, G1, and if you do for G2, G2 is this particular curve. It is lying inside the feasible region. So G2 of x star will be strictly less than 0. So when you have scenarios like this, whenever it is equal to 0, this will be included in my active constraints, and this will not be included. Yeah. So it means the constraint is so this is your constraint. So whenever you say, let's say we have constraint something like x square plus y square less than or equal to 1 or something. So if you represent that on your domain, so if a particular point satisfies this constraint, which means x square plus y square is exactly equal to 1. So if it is some circle like this, then that particular point x star, y star, whatever is that point, is lying on the boundary of it. Yeah, radius is 1. So if you write it in GA of x, it will be something like x square plus y square minus 1 less than or equal to 0. This will be my GA of x, right? So when I am saying it is equal to 0, like GA of x equal to 0, it means that particular point is lying on that curve, lying on the boundary. So it's not an interior point. No, no, this is GI. This is GI. So when GA of x equal to 0, it means x square plus y square minus 1 equal to 0. Yes. Yeah. So those constraints are called the active set. So those constraints form a set called active set. So these constraints are the active constraints, and these are the only constraints that we need to be used in the solving whenever we are solving the problem. Because once you know that wherever these are equal to 0, then you have equality, all these equality constraints. So with these equality constraints, you can directly simplify your problem, because since it will be equal to 0, you can reduce the number of your variables and then do other tricks that we have discussed previously. And there are other ways as well, which we'll see in KKT conditions. So now we define these constraints. The way we define these constraints, we are representing in this way, like GA of x less than or equal to 0 in some set of equations. And then we defined previously that we need to find d somehow, and then we need to come up with some way, like at every point we have to calculate grad f, and then we have to do the dot product with d, and then say whether it is greater than or equal to 0 or not. If it is satisfied, then that filter we will use, and out of all those points we'll again find whichever that. How to do the second step we'll do later. But now the question is, how do I get my d? If I get d, I can do this thing, but how do I get my d? So By definition, D is essentially tangent to the S. Like if S is my feasible region, D will essentially represent a tangent, all the vectors that are from any point. Like this is my feasible region. If there is a point, internal point, then all the vectors from which I can reach that particular point will form my tangent cone. If it is an external point, then all the vectors, again, only from the feasible set you have to take. So all these vectors are D. So essentially, how do you find how do I get this set? Is you define, you take the normal first. So let's say this is g of x less than or equal to 0. So when you take the gradient of, I just draw this again, so there is no confusion. So this is g of x less than or equal to 0. So when I take a gradient of it, the gradient will always point in the direction of increasing function. So if this is less than or equal to 0, so this will be my grad g. It's like as you keep going in this direction, you keep going into the positive one. So this will be my grad g of x. Now how do I get my d? So let's say I take a vector d. Let's say this is some vector d1, and there is another vector, say d2, and let's say d3. This d3 is, let's say d3 is perpendicular to grad g. So if you take the dot product with grad g and d1, d2, and d3, out of this you can clearly see here that there is an acute angle between d1 and g. So grad g times d1 will be positive. Grad g times d3, if it is perfectly tangent, it will be 0. And grad g times d2, it is an obtuse angle, so that will be negative. So by definition, what we want is all the vectors such that the vectors will be in the interior of this set S. So which means all the vectors that are over and above this particular point, all these vectors. So essentially we will remove this point. This vectors and this vector will essentially form a tangent cone. So all I have to do is take the gradient of G and then choose those vectors such that grad G times D is less than or equal to 0. Then that particular set D of vectors is my tangent cone. That's how you construct the tangent cone. Again, now again we were saying like all constraints are not important. Only the active constraints are what are important, because the remaining constraints whatever are there, and whenever I'm saying the feasible region, and that they are anyway going to be feasible. So again, even G, the way you represent your boundary can be again in different ways. It's not like one equation cannot always define your boundary, especially when you have these active constraints. Whenever you have an active constraint, G will be essentially equal to 0. So for example, you can take the constraint something like x plus y equal to 1, something like this. The way to represent this particular boundary is this equation. You can also represent the same equation maybe in multiple other ways. Maybe you can add something like maybe you can take something like this equal to 0. That will also give me the same equation. I can take higher order powers and all of them will be equal to 0, and all of the equations will represent only the same line. All of them will give me the same line, all the points on the same line. But when you take gradient of this one versus this one, the values of the gradients will be different. So just to ensure that the way we get the value of D in a unique way, we'll give that, we'll put an extra qualification on our constraints. The way when we define the constraints, they have to be defined in such a way that these gradients of the vector have to be linearly independent. And there is another way to interpret this. So think of this as when I told previously that when you have multiple surfaces, not just one constraint, when you have multiple constraints, and then you take an intersection of all these constraints, and then you want to find the tangent cone of the intersection of all these surfaces. So for that, we have to actually consider all the surfaces and then create an intersection and then do this and then represent that. So for example, if you have multiple constraints like this, when you have multiple constraints like this, and this is the intersection of all these constraints, so you have to find a way to first solve all of them and then somehow find a representation, some mathematical equation to represent this particular surface, and then you have to find the tangent cone for it. That might always not be possible. So what we are doing now instead is we will take the original equation as is. We will find the tangent cones for say 1. We will find tangent cones for 2 and 3, and then we do an intersection of all these things. And now again, if you see, why we are worried about active constraints again is whenever you have an active constraint, that's when g of x will be equal to 0. And for all the inactive constraints, g of x will be less than 0. Whenever, which means that particular point will be interior for that particular, say, let's say 3, this particular 3 is an inactive constraint. Let's say 3 is an inactive constraint. So the point is something like this. This point will be lying on 1. So it will be 1 is an active constraint. 2 and 3 will be inactive constraints. So when you have an inactive constraint, g of x will be less than 0. And if I find the tangent cone for this particular point, at this particular point, what will it be? Because it is an interior point, it will include all the directions. Again, for 2, it will be all the directions. So and only for 1, it will matter because only few points will be included. Only these points will be included, and any point outside of 1 will not be included. So when I take an intersection, the only one that is important is just the active set. So whenever only the active constraints is what will decide what the tangent cone of the intersection surfaces will be. And again, to ensure that uniqueness, as I said, like to remove this inequality, we need some way to define uniquely the tangent cone. So that is where we get the concept of this linearly independent system. So when you have a linearly independent system, then all of us follow the linearly independent system. Then the way we define this D will be a unique one. For those particular linearly independent constraints that we have defined GI, and again, only just the active constraints will give me the this particular D. Once I get the D, then I can use them inside my, like I can use it along with my objective function to determine how to filter out the points that are not necessary to be evaluated. Okay, clear up until here? Anything else in? Yes. Yes. We don't have to worry about less than 0 thing as of now. Okay. So to put this simply in the way that we have to define is put both of these together. So in the tangent cone, we have two things. So one is for the constraints is we have grad g times d less than or equal to 0. And for the previously to be a local minima, you have to satisfy grad f transpose d greater than or equal to 0. Now putting these two together and using Farkas lemma, which I am leaving you, like you can actually go through the lecture videos. Once you do that, the expression that you get is something like this. So it is very similar to your Lagrange thing. So you take grad f plus summation of lambda I times grad gi equal to 0. So this we have done. This again comes in KKT conditions as well. So this condition is what should be satisfied for getting a local minimum of a function f. Or to put more in general, when you have like this in general, we define it for say KKT conditions where you have to minimize some function f of x such that you have these inequality constraints, and let's say both of the functions are continuous and first order differentiable. Let x star be a local minima and a constraint qualification is satisfied at x star. Then there exists a lambda I greater than or equal to 0 where I is only the set of active constraints. Again, here also we are saying active constraint. If it is not active constraints, then we will need to use complementary slackness condition that we will see. Okay, but for now, let's say we'll take only the active constraints. Just for the active constraints, you have grad f plus this lambda times gi equal to 0. So this is my KKT condition where a is all the constraints where gi equal to 0. This just putting together everything. Now, for example, instead of writing it in this way, where I belongs to set of active constraints, I can include all the inequality constraints also. So from I equal to 1 to m, I will include all the inequality constraints, make them equal to 0, but then add an extra condition saying lambda I times gi equal to 0. Now here you will be having two possibilities where you can either have lambda I equal to 0, you can have gi of x star equal to 0. Yeah, of course you can say both of them equal to 0, but let's take these two scenarios. Out of these two scenarios, whenever you have gi of x star equal to 0, then that is an active constraint. So that's so you have to determine lambda, you have to solve for lambda. Whenever g of x star is less than 0, this condition will ensure that particular lambda will be 0, so that won't enter this equation, because whenever you have gi less than 0, that is not that is an inactive constraint, so you don't have to worry about that particular constraint. It's essentially the constraints that will drive your optimization problem. So if some particular constraint is inactive, then you don't have to worry about it. So that should be somehow eliminated from whatever we are doing in the optimization problem. So this will ensure, this complementary slackness will ensure that that will go off the problem. So you will not be solving anything regarding that. So this is just with an objective function with a set of inequality constraints. Now when you have equality constraints as well, then you will have one more term that will be coming over here. We will see in the end. So So before go, maybe I'll show that as well. Okay, I think I have not included it, but when you have a set of equality constraints, then you have the summation over equality constraints as well. Some theta times whatever constraints you have. If you just have linear constraints, then it will be ax minus b. There is no sigma. Let's say this is just a matrix. I'll put everything in one matrix and write it in as a matrix product. The next concept is the convex function. So why we are worried about this convex function is just to simplify some of the scenarios, as in some of the existence things that we don't have to worry about. Like initially, as we started out, before even trying to solve for an optimization problem, we need to be sure that some optimal solution exists. Only if it exists, then we can do some method, and whatever solution we go to, we will see that okay, it might be an optimal. So but knowing that a function is convex will give us some tools to say that a solution, some optimal solution exists in terms of a global minima, local minima, something will exist. So the definition is the same as before. So you take a function f mapping from R into R, such that if f of alpha x plus 1 minus alpha phi is less than or equal to this particular alpha into f of x plus 1 minus alpha into f of phi, where alpha belongs to 0 comma 1, then that particular function is called a convex function. And you can use a Taylor's expansion and you can get a similar thing like this, where you have f of y equals to some higher order terms. So what we are saying is, if you just use a linear approximation around a point y, then that particular linear approximation versus the actual function value, the actual function will always be greater than or equal to this one. Or to put it in a simple way, you can add one more term here, the second order derivative. So the Hessian will come into picture. That Hessian will always be a positive semi-definite one. So either way, so the idea is this is some criteria to check whether that particular function is convex or not. So let's say you know the function is convex. So what is the advantage is, when you know a function is convex, then you have let's say linear equality and some inequality constraints, and all these functions are all the objective as well as your constraint functions are convex. Then you know for sure that when you try to find a minimum of this, that will be a global minimum. So the existence is kind of solved when you know it is a convex function. For convex functions, if you find a minima, then it is going to be a global minima. And how you solve the problem is you take the Lagrange function as f of x plus summation of all this lambda a gi plus theta transpose ax minus b, and then you take gradient of this, make this gradient equal to 0, take the gradient with respect to the decision variable x equals to 0, and then you also have the complementary slackness conditions. You need to satisfy this such that only the active constraints will actually be involved in solving the problem, and inactive constraints will be removed from the problem. And yeah, this doesn't need to be linear. You can also have nonlinear equalities. Then all you have to do is this will again be a summation, some j equals to 1 to p, whatever those are, theta j times a j of x. But as we have seen, like when you have some convex, we can somehow discretize into some set of polyhedrons, and then you can eventually convert all those things into this particular form ax equal to b, and then you can solve it. Some way to linearize these constraints, and you can always convert it into a set of linear problems. You have some question? Yeah. I didn't get your question. So no. So you're saying x square plus y square. Let's say f of x. You are saying objective function is something like this. Yeah. So do you mean the objective function or the constraints? Which one you're saying? Yeah. Okay. Yes. Yes. So something like this you're saying. Okay. Hmm. No, this is for a special case that your f has to be a convex function. If your f is not convex, then this is not true. So let's say you have a function something like x square plus y square, some parabola or something in 3D. So is this convex? Okay, I think x square plus y square is convex. So let me take something like x cube plus y cube. Is this convex? Let's say for all x comma y belongs to R. Oh, how do you check it? So you just calculate the Hessian. So what will be the Hessian? The gradient of f will be something like 3x square and 3y square. And if you take Hessian, be 6x, something like this. So this will be positive definite only in the first quadrant. So for all x, y belongs to R, it is not a convex function. So there is no guarantee that you will have a global minimum or something. This is only for a convex function. Only when you have a convex function and then that particular convex function satisfies this particular equation, that gradient of this particular Lagrange equals to 0, and also your complementary slackness conditions has to be satisfied, then you will have a global minimum. If you have a minima, then that will be global minima. And these are essentially like your KKT conditions. So when if the KKT conditions are satisfied for a convex function, then it will have a global minimum. Okay. Yeah. So this is more with the concept. So there are no questions, then we can take some problems. I just want you to answer some of these problems so that just to ensure that everything you're clear. Just go through the problem and then you can tell me the answer. So there is a set S where x is in R2 such that 0 less than equal to xi less than equal to 2, and I have a point 1 comma 1. Which of these points are contained in the tangent cone of this particular point and this particular feasible region? These are essentially again since it is in tangent cone, these are not points, these are vectors. Like 1 comma 0 is essentially a vector, 0 comma 1 is a vector, 0.5 is a vector, 0 0 is again origin vector. So which of these belong to the tangent cone for this particular feasible for this particular domain? Yes, or this particular region? Yes. How do I do that? Yeah, all of them. So how do you do that? You just, yeah, you can just say, okay, since all of them are in the feasible region, no, you don't have to worry about anything. It's actually something like because 1 comma 1 is inside the feasible region, so any vector will actually be the tangent cone. If instead of 1 comma 1, if I would have given something like this, let's say 2 comma 2, then what would you say? Let's say this is not 1 comma 1, let's say it is 2 comma 2. Then what can you say? No. If I am at some point here, so you're saying 1 comma 0 is a vector like this, 0 comma 1 is a vector like this, 0.5 is a vector like this. How will it be in the tangent cone? Yeah, it's an extreme point, right? How will it be? Okay, let's take a point here. Let's say something like 2 comma 1 and 1 comma 0 is something like this. It wouldn't be inside it, right? Whatever tau k you choose, it wouldn't go inside, right? Because if you take a point here, then the entire vectors will be something like this. All the vectors Only these vectors will be in my tangent cone. Anything other than that that's going outside the feasible domain, that is pointing outside towards outside of the domain, will not be in the tangent cone. Just because this particular point is lying inside the domain, all these things are actually contained in the tangent cone. Clear? Yeah, 2 comma 2 is there. Now this is a vector. So this vector should point me from that particular point towards the interior of the domain. Then that particular vector will be included in the tangent cone. So if I consider say 0.5, 0.5, that will be pointing out towards outside the domain, right? No, these, yeah, no, 0 comma 2 is 0 comma 2 is different. 0 comma 2 is a point. Tangent cone is the set of all vectors, right? It's not set of points. It depends on the point you are considering. What is the point you are considering? This point? Tangent cone is defined. Okay, at this point you are saying, then to j cap will be something like this, and it will be pointing outward, so that will not be in the tangent cone at this particular point. I didn't get, so you're saying if you put it here, even then it wouldn't be pointing inside the domain, right? Because the point here is 0 comma 0. Okay, so I think I understood what you were trying to say. So you're trying to say like this particular vector, whatever you have, I will translate it to this particular point 0 comma 0. Yeah, let's say you translate it to here. So, but then the tangent I'm considering here should be at this particular point. So the vector, like the way we defined it is xk minus x star by tau k, right? So my origin is situated at x star. Like the way we defined it is origin is situated at x star. But when you shifted it, the origin would move, right? If you move both of them here, then it will be changed. Yeah. So essentially, then you would be defining it at 0 comma 0. 2j cap will be in the tangent cone at 0 comma 0. So like that's why we have included x star in the definition of tangent cone. Like when we define that set, 1 1, x star is here. That is an internal point. Because it is an internal point, all the directions are actually inside the tangent cone. Yeah, yeah. These are vectors. These are not points. Yes, these are d's. These are all vectors. So the following, maybe I should write here. Yeah, if it's a boundary point, then the answer will be different. Then all of these are not there. Okay, maybe for this word, hey, let's say you have a circle, x1 square plus x2 square less than or equal to 1. The tangent cone of s at the point 1 comma 0 is a singleton set. Is this true or false? So you have a circle. Oops, okay. I think it will fit correctly. It's not fitting correctly. So the entire region inside my circle is the feasible region, like is my set yes, and I have a point 1 comma 0 here. So what are the tangent? What is the set of tangent cones for this 1 comma 0? All these vectors. All these vectors will actually form a tangent cone, right? So is it a singleton set? Because it's not like the cardinalities are not one. False. I mean, you just have one element in it. False. Okay, this is a straightforward thing from the from the theorem that I stated before. Let's say you have to minimize some function f, x belongs to s. Suppose for some exponent belongs to s, we have this less than 0. then is extra the local minimum of the problem? Or extra is the local minimum of the problem, is it true or false? False. This question is just to help you recall whatever we have done. Again, the logic goes like D always points towards inside, and I'm trying to find minima. So del F, if del F is increasing along the direction of D as I go inside, then F will be a local minima. So this should be greater than or equal to 0. That is what we have defined. So this, since it is less than, it will be false. If instead of minimization, if it's converted into maximization, then it might have been true. Again, you have to have the equality also. But okay, let's take this problem. This is also a straightforward one. So you have to minimize this function subjected to these constraints. How many of these constraints are active at a particular point x star? So there are 3 constraints, let's say A, B, C. Which of these are active at this particular point? Again, whenever we say an active constraint, we need to define the point x. If I have not defined what the point x is, then you cannot say anything. Depending on the point x, that constraint can either be active or inactive. So for this particular point 2, 1, which of these are active? How do we decide? Is we just substitute that in that particular equation and check if g of x star equal to 0. If that is satisfied, then that is an active constraint, otherwise it is not. So you can just substitute it and you can quickly tell me. Yeah. So the same equation. Now, is the constraint qualification satisfied? So again, I am saying linearly independent constraint qualification. So what do I have to do here? What has to be linear? No, constraint is not linear. Okay, that is fine. But this is linearly independent constraint. The qualification theorem states that my grad g is what has to be the linearly independent, right? Again, as I said, these have to be defined at a particular point. As a point changes, this keeps changing. So at that particular point, you calculate grad g, that particular values, whatever you get, those values have to be linearly independent. It's not like everywhere you don't directly substitute x1 square this and then try to find the linear independence between these quantities. So let's say this is g1, g2, and g3. Again, for constraint qualification, we just need to consider only the active constraints. So first to check for the active constraints. So 2, 1, okay, this is active, this is active, this is not. So these two conditions, you calculate del g1. So that is 1, 3. Let's say 1, I'll just put it as matrix 1, 3. And you calculate grad g2, which will be 2x1 and 2x2. You substitute the point, then you get a vector. And these two vectors are what that have to be linearly independent. That is what the constraint qualification states. And of course, this has to be true for all the points inside the domain. But this particular question asks you whether it is satisfied at this particular point or not. So at this particular point, they are linearly independent, right? Yeah. This is again a straightforward one that we have just discussed. If x star is a local minimum for a convex function, then x star is also the global minimum provided the function f is convex. If it is a convex function, then it is going to have the global minima, then that will be the local minima as well. Okay, what about this? A convex function always has a unique minimum. Is it true? It will have a global minima, that is clear, but will it always be a unique one? By unique, what we mean by unique is not be. So why do you? So when we say unique minimum, is essentially you can when we define the convex function, we told that the Hessian has to be positive symmetric, right? So there can be points where you have multiple x star values, like you have f of x, something like this. You can have multiple x values, x1, x2, x3. All of them might give you the same value of something like f of x1 equal to f of x2, and all of these will be equal to each other. All of them will be equal, and that is the global minima. But these individual x values that you are choosing might be different. But the objective function value will actually be the same. So this we have just discussed. Okay, can answer this. So the function is f of x1 x2 is x1 cube plus x2 cube, and we obtain a point at which grad f equal to 0. X star is a global minimum. There are no constraints. So when you try to apply the KKT, all you have to do is first get the Lagrange. Since there are no constraints, the Lagrange will be grad f. Sorry, Lagrange will be equal to f. So that particular thing equal to 0. So and I'm saying x star is global. This will be true only if this particular function is convex. And this will be convex only when, just like if you calculate the Hessian of this, you will get something like the Hessian of this will be 6x1. This particular thing will be positive semi-definite only when x1 x2 are greater than or equal to 0, which means only in the first quadrant. So only in the first quadrant it will have a global minimum, but here since I did not specify any constraints, this is not a convex function, so this may or may not be true. I mean, it won't be true. X star may not be the global minimum. Is this clear? Positive semi-definite. You need to have x1 and x2 greater than or equal to 0, right? In the first quadrant. No, when you define a convex function, you have the constraint that f of y greater than or equal to f of x plus grad f transpose times y minus x plus something, right? Plus this Hessian term and other terms. So this greater than or equal to 0 will be there if this is positive, right? This is just to say that it is like when you take the linear approximation, it should that particular value is less than the original function value. So maybe this should be something straightforward. So there are two sets, S1 where with this particular equation and S2 is a different equations. And my particular point is 0, 0, and I want to do the tangent cone for intersection of S1 and S2. Is it a line? What is my S1 and S2? One is a circle around 1, 0. And another one is a circle at -1, 0. And I'm going to take intersection of them, that is only 1 point 0, 0. And for this particular point, I want to find the tangent cone. What will it be? Okay, so you don't want to include 0, 0. I mean, every tangent cone is a cone, so cone will always have origin in it. So it won't be a null set, right? Yeah. So it will have only one point, and that is 0, 0. So it is not a line. Clear, right? Yeah. Okay. So we have two local minima for a convex function. Which of the following are correct? You should answer this one. We have discussed all of this before. So B, C, D. Yeah. We have just discussed that even when you have multiple minima, all of them need not be equal. So this may or may not be true always. But since it has to have a global minima, whatever local minima you have, the objective function should be same for all of them. So this is true. They are global minima for sure because it is a convex function. And what about the last one? When you take a 0.5 x star plus 0.5 y star, how did you come up with this? It's a global minima. How? Yeah, for it to be convex, when you take a linear combination. So by definition, we have 0.5 x star plus 0.5 y star should be less than or equal to 0.5, something like this. This is by the definition of convex. And now you know that both x star and y star are the global minima. So f of x star and f of y star should be equal. And this will be something like some f, let's say the optimal value, f star. Since that is a global minima, it cannot be less than it. So the only possibility is it has to be equal to f star. Now this is the last question I have. So it is a convex function subject to this. This I have just discussed. And if it satisfies all the KKT conditions, then extra is a global minimum of the optimization problem. The most important criteria that we have to check is it has to be convex function. Only if f is convex, then you have and that particular extra satisfies the KKT conditions, then extra can be called the global minimum of the optimization problem. Of course, I should have mentioned here that G also needs to be convex. Just put G also here. Well, even both the constraints as well as your objective function, both are convex functions, then you'll have when you solve for the KKT conditions, like a particular point satisfies the KKT conditions, then that particular point will be the global minimum of the optimization problem. Yeah, these are the questions I have to fix for this week. Do you have any queries? Or do you want me to discuss something? We have actually more than 1 hour left here. If you have any questions, we can discuss them. Not then. Second last week assignment. Okay. The one that is posted on the website or the one that we discussed? Oh, the assignment questions. Can you share your? Is the solution out? Oh, you have a doubt in the solution. Can you share your screen or something? Yeah. Yeah. Yeah, I can see your screen. Consider the following network. So 12th question or 11th one? Which one? 12th question. Okay. Yeah. So you have a source S and some S target T, and you have some network given to you. For the minimum cut problem, the optimal cut is produced for the partition. So the partition means S, A, C, and D are belonging to one set, and B and T are belonging to the other set. What is the maximum flow from source to sink? Okay. So the both minicut and max flow problems are primary and dual problems, right? That is clear. So now what are the connecting links between these two partitions? You just put 1 second. I'll just note it down and then I'll draw it so it will be clear. I can write it and show you. So you have S, A, B, C, E, and target 16, 13, 10, and 4. It's 4, 2 to 6, 9, 2 to is 14, 7, 20, 22 is 4. And your partitions are S, A, C, T, P, and T. And you need to find the maximum flow. Okay. Yeah, I'll just share my screen. Yeah. I don't have this one. My screen name will be shared. You can see my screen, right? You can see my screen, right? Yeah. Yeah. So yeah, so this is my source and target, and whatever is on the link is basically the maximum flow that can happen through that particular link. So from S to A, 16 units can be transferred, or that is the maximum capacity of that particular link. So when we do an optimal cut, like min cut problem, what we are trying to do is first we need to segregate into 2 points. So this they told S, A, C, D are, so these four things they are saying they are belonging to one branch, and the remaining else are something else, which means you are cutting something like this. And what he is asking is, when you cut like this, what is the maximum flow that can happen? So where is the flow happening? The flow is essentially like when you cut something, the flow only, like we have defined it previously. Like whenever you have a cut, like Wij when we define, this can be either 0 or 1. If 1 is for the edges that are included in the cut and 0 for the ones that are not included in the cut, and then your objective function is something like sigma Cij times Wij is your objective function. So this is what we are trying to find, but we are trying to minimize, sorry, we are trying to maximize or something, right? So whatever the cuts that are there, so let's say this cut is there here. This is one cut. This is another one. C to D is C and D are belonging to the same set, so that is not there. And then what other sets you have? B to D, B to S there is no connection. B to A there is one connection. B to C there is one connection that we have cut, and B to D there is one connection we have cut. So like you take one by one. So B to S, B to A, B to C, and B to D. B to S there is nothing. B to A there is one. And B to C there is one. I'm just putting minus sign here because it is in the opposite direction. And B to D there is something else. Similarly for T we can say T to S, T to A, C and D. T to S there is nothing. A there is nothing. C there is nothing. T to D there is something. So what is the maximum flow that can happen through this particular cut? 11, 20, 22. Oh, did I miss something? Okay, let's try Wij. I think I missed something. What are my Wij? S, A, B, C, D, and T. Similarly, we take S, A, B, C, D, and T. So this is my big matrix. So let's say if I write the Cij matrix, S to A, S to B, S to C, S to D. This part is clear to you, right? Whatever I'm writing here. Yeah. A to A, A to B, A to C, A to D, A to T, B to S, B to A, B to B, B to C, B to D, and B to T. S to S, S to A, sorry. C to C to S is 0, C to A, C to B, C, C to D, C to D, D to S, D to A, D to B. If I write something wrong, just let me know. D to C, D to D, and D to T. From T, there is nothing going, so everything will be 0. This is my Cij matrix. Now let's try Wij matrix. So which of these sets are there in the cut edges? S2S. Both are in the same set, so Wij is 0. S2A, S2B, S2B, S2C, S2D is same set, so 0. S2B is 0. A2S, A2A, A2B, A2C, both are in the same set. A2B, no connection. A2T, no connection. Yeah, but both are in the same set. So like this Wij will be one only if they are in the different sets. Like the connection should be from between different colors. Okay. B2S, B2A, B2C, sorry, B2B, B2C, B2B, and B2T. Then what else we have? C2S, B2A, B2B, B2C, B2D, B2T, D2S, D2P. Both are different colors. D2C, D2T are also different colors. From T, we don't have anything. You have to just take a dot product of this and do the summation. So 1 into 12 plus 1 into 9 plus 9 plus 1 into 7 plus 4. Yeah, it's the same thing. 21 plus 11, 32. I think the answer is something. Okay. Okay, I'll get back to you on this then. Which problem is this? 12, right? Okay. Anything else? Hmm. So, but the solution is already provided, right? So, can you share me the solution? Can you share the screen? Yeah. 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 Yeah, I can see it. I can see this one. You can just maximize the width of this one. 12 plus 7 plus 4. What are the ones that you have excluded in this? So 9 is excluded from it. So where is 9 is the connection between B to C. Okay, there. Okay, it's in a different direction. B to C is in a reverse arrow. Okay, that's why they've excluded it. Okay. So where is B to C? Why didn't I exclude it when I written it? B, sorry, you told you have another doubt as well, right? Yeah. Yeah. Okay. One second. Let me read the question. Consider the shortest of problem with m nodes and n edges. The LP formulation can be matched linear sequence process subject to Ax equal to B. Okay. Let's use the cost of each edge. And A is an n cross n matrix. Which of the following is true about A? Every row has exactly plus 1 and 1 minus 1, all others are 0. Every column has exactly plus 1 and minus 1, all others are 0. Okay, when we have written the equation last week, so how did we get the equations? Let me just share the screen. Yeah, you can share, stop sharing. This is what we got, something like this, right? It's something similar like this problem. So I have certain nodes, some edges, I wrote down all the equations. You can see my screen now, right? Yeah, when we wrote the equations, we got something like this. So the question was asking you specifically like if you take the row by row, the rows can be ones, minus ones, zeros, everything are zeros. So what was that? So what was the other option? Every column has the same. So, but even the rows are the same, right? But no, right? First row has both one and minus, like it has only ones. It doesn't have a minus one. But if you take a column, then definitely there will be a minus one somewhere because the conservation has to hold. If something is going somewhere, it has to come out. If you, yeah, we have it. But you are saying it has to have both one and minus one. Third row we have, but the first row we don't have, right? Yeah. I think they were asking specifically like every row will definitely have plus one and minus one, something like that. Is something like that written? Like I'm asking you, I do not know. I have so in the question did they tell you that it has to have definitely one, like some plus one, minus one, zero, all three elements have to be there for sure. That's how they have written the question, the option. Okay. Okay, then that is not true, right? Because I have a row with that doesn't have a minus one in it. So let's just check that. So let's take first column. Where will the minus one come in first column? You have to just check these equations. So there is xbd coefficient that you have to check. Xbd coefficient is nothing. So this is 0. You check xcd coefficient, xce coefficient, xcf coefficient, xdf coefficient, xeg coefficient. I mean here you don't have it, right? Okay, I removed this one. So you have minus one here actually, right? No, but I can always convert it into plus one. So did they say anything about B, that B has to be positive or something? We didn't put the extra constraint. Okay, those will also be added here. So basically x less than equal to 1, you will again make x plus s equal to 1, and then those s will also be added to this, and then that will equal, essentially again become the same thing, right? X greater than equal to 0. Okay, with these extra constraints, what will happen? Let's say we added these extra constraints. All those constraints will add extra ones here. Where will the minus 1 come from? Yes, what did they say in the solution? They just told, what did they say in the solution? B has to be positive. Yeah, you can share. Yeah, that's what I also thought previously, but then we did something wrong in the problem. If there is some inflow, there has to be some outflow, so there should be some 1 and some minus 1. So what is the mistake in the problem? I think I changed the minus 1 to plus 1. That's where the problem came. That b, when we multiplied with minus 1, it got reversed. Otherwise, everywhere it will be minus 1, 1, something like that, right? Any other questions? The other one was clear, right? The graph one. The graph question is clear, right? Yeah. Okay. Thank you. Thank you for joining. So I think if there are no questions, then we can end the session for today. We have around 45 minutes left, but I think there is no one else. Okay. Okay. Thank you. Thank you for joining. We'll meet next week.